Now question number 2 is, let alpha be a real number. Consider the function gx, which is alpha plus mod x square e to the power 5 minus mod x square for x belongs to R. Now the first part is, determine the values of alpha for which g is continuous at all x. Now we know that mod of x, it's a continuous function. Exponential function, it is also continuous. Any polynomial function is also continuous. So their composition and their product will also be a continuous function. So this gx, it is continuous for all x for alpha belongs to R. So whatever may be the value of alpha, this function will always be a continuous function. Now the second part is, determine the values of alpha for which g is differentiable at all x. Now for the second part, we can express this definition gx as alpha minus x whole square into e to the power 5 plus x square if x is less than 0, and it will be alpha plus x whole square e to the power 5 minus x square when x is greater than or equal to 0. Now this first part, function is continuous and differentiable, and the second part also, this function is continuous and differentiable. Now there is a definition change at 0. So we just have to check differentiability of this function at x equals 0. Now what we'll do is, we'll find g dash x when x is less than 0. So if x is less than 0, then g dash x will be alpha minus x whole square e to the power 5 plus x whole square into 2, 5 plus x, and then plus e to the power 5 plus x whole square into, this is 2, alpha minus x into minus 1. If we find its left hand derivative, now its left hand derivative at 0, which is g dash 0 negative, it will be alpha square into e to the power 25 into 10 plus e to the power 25 into minus 2 alpha. We can take e to the power 25 common, then we can write e to the power 25 and then 10 alpha square minus 2 alpha. Now we'll find derivative of this function when x is greater than or equal to 0. In that case, g dash x will be alpha plus x whole square e to the power 5 minus x whole square into 2, 5 minus x into minus 1 plus e to the power 5 minus x whole square into 2 alpha plus x. Now we'll find g dash 0 positive. It will be alpha square into e to the power 25 into minus 10 plus e to the power 25 into 2 alpha. Now again we'll take e to the power 25 common. So we'll get minus 10 alpha square plus 2 alpha. That's your right hand derivative. Now this function will be differentiable at x equals 0 when left hand derivative is equal to right hand derivative. That is when e to the power 25 10 alpha square minus 2 alpha, it is equal to e to the power 25 minus 10 alpha square plus 2 alpha. Now e to the power 25 will cancel, so we'll get 10 alpha square minus 2 alpha equals 0. That is, the value of alpha is either 0 or The value of alpha is 1 by 5. So this function gx will be differentiable when alpha is 0 or alpha is 1 by 5. Now question number 22 is, for n greater than or equal to 2, fx is defined as x to the power n into mod x. We have to find the points where this function f is differentiable. Now we can write this function fx as minus x to the power n plus 1 when x is less than 0 and x to the power n plus 1 when x is greater than or equal to 0. Now f0 negative will be 0, f0 positive is 0 and f0 is 0. That means this function f is continuous in x belongs to R. Now if we find f dash x will be minus n plus 1 x to the power n when x is less than 0 and it will be n plus 1 x to the power n when x is greater than 0. Now f dash 0 negative, it will be minus n plus 1 0 to the power n. Now since n is greater than or equal to 2, this value will be 0. In the same way we can find f dash 0 positive, so it will be 0 to the power n, which again is 0. So left hand derivative at 0 will be same as its right hand derivative. That means this function is differentiable everywhere, and that's your option C. Now question number 25 is, we are given this function such that f3 equals 3 times f dash 3 and it is a positive number. Then this limit x tends to infinite, f3 plus 3 upon x upon f3 to the power x is. Now if we look at this form is 1 to the power infinite form. And for 1 to the power infinite form, we have this shortcut that we can express it as e to the power, this limit x tends to infinite, gx into fx minus 1. So it will be f 3 plus 3 upon x upon f3 minus 1. So we can write this limit as e to the power limit x tends to infinite, f 3 plus 3 upon x minus f3 upon f3 1 by x. Now what we will also do is we'll multiply by 3 and divide by 3. Now this is nothing but this is f a plus h minus f a upon h, and that is nothing but derivative of this function at a. So we can write this as e, and it'll be 3 into f dash 3 by f3. Now in the question it says 3 into f dash 3 by f3 is 1. So this value, it is equal to e to the power 1, which is e. So this limit, it exists and is equal to e, and that's your option B. Now question number 2 is, let R denote the set of real numbers. Find all the functions f R to R satisfying mod of fx minus fy, and it is equal to 2 x minus y. Now taking x as x plus h and y as x, we can prove that this function is a continuous and differentiable function. Now if we write this function as fx minus fy upon x minus y mod equals 2, and if we take this limit y tends to x, then we get mod of f dash x, it is equal to 2, or we can write f dash x equals plus or minus 2. Now we'll integrate this function. We can write this as fx equals plus minus 2x plus c. Now question number 1 is, for any polynomial pt, the limit t tends to infinite pt upon e to the power t is independent of polynomial p. Justify the statement and find the value of this limit. So we have this limit, which is limit t tends to infinite p as a function of t upon e to the power t. Now if we put t as infinite, this numerator will be plus or minus infinite, and then e to the power infinite will be infinite. So when it is infinity upon infinity form, we can use L'Hopital's rule. And if we use L'Hopital's rule, we can write this as limit t tends to infinite p dash t upon e to the power t. Then again it will be plus minus infinity upon infinity. So we can differentiate it again. We can keep using L'Hopital's rule till we differentiate this function n times, which is degree of this polynomial. And if we differentiate this polynomial up to its degree, then it'll be some constant upon infinite, and any constant upon infinite is simply 0. So this statement is true and the value of this limit is simply 0. So that's your part A. Now part B is show that q dash 0 exists and find its value. And why is it enough to calculate the relevant limit from only one side? Now we'll find q dash 0 positive. Now q dash 0 positive will be limit h tends to 0, q 0 plus h minus q0 upon h. Now this is limit h tends to 0. Now q h positive when x is greater than 0 is simply e to the power minus 1 by h. q0 is 0 and here it will be this h. So we can write this as limit h tends to 0, 1 by h, and then e to the power 1 by h. Now what we will do is we'll let 1 by h as t, then we can write this as limit t tends to infinite t upon e to the power t, which is of the form pt upon e to the power t, and we know that this limit is equal to 0. So q dash 0 positive is 0. Now we need not calculate q dash 0 negative as this given function is an even function. So suppose we have to find the value of q minus 2 will be e to the power minus 1 by 2, and which is same as value at 2. So this given function is an even function. So we just have to calculate limit from only one side. So this q dash 0 exists and its value is simply 0. Now part C is for any positive integer n, show that qn0 exists and find its value. Here qx is the function in part B and qn0 denote the nth derivative at x equals 0. Now what we'll do is for this part C, we have to find nth derivative of this function at 0. Now we know that qx, it is an even function. Now if qx is even, q when x is odd, q2x is even and continues. So we can say this q and x will be even when n is even, and it'll be an odd function when n is an odd function. So we can simply write qn minus x will be minus 1 to the power n q n x. Now if we look at this function, which is qx, when x is greater than 0, it is e to the power minus 1 by x. Now q1x will be e to the power minus 1 by x into 1 upon x square. Now if we find q2x will be e to the power minus 1 by x minus 2 upon x cube plus 1 upon x square e to the power minus 1 by x, and then 1 by x square, which is e to the power minus 1 by x minus 2 upon x cube plus 1 upon x to the power 4. Now we keep differentiating it. We can write qnx will be of the form e to the power minus 1 by x and then some polynomial expression of 1 by x. Now if we have to find qn0 positive, it will be this limit h tends to 0 e to the power minus 1 by h p 1 by h. If we let 1 upon h as t, we can write this as limit t tends to infinite pt upon e to the power t, and this we have already established in part A that this is equal to 0. So from here we can say this qn0 positive will be equal to qn0 negative and it will be equal to 0. That is, this qn0 will exist and it is equal to 0. Now question number 30 is, find the set of all points where this function is differentiable. Now numerator is differentiable for x belongs to R. Denominator is differentiable except for x equals 0. So this function will be differentiable for all x except at x equal to 0, and at 0 we do not know whether it is differentiable or not differentiable. So we have to check its differentiability at x equals 0. Now if we check its left hand derivative at 0, it will be limit h tends to 0, it will be minus h upon 1 plus 2 mod h minus 0 upon minus h. Now this is 1. And g dash 0 positive will be limit h tends to 0 h upon 1 plus 2 mod h minus 0 upon plus h, and which again is 1. So this function is differentiable at 0. So this function gx, it is differentiable for all x belongs to R, and that's your option A. Now question number 4 is, the function f is defined on R to R and let it be a twice differentiable function such that f dash x minus f dash y will be less than or equal to 3 times mod of x minus y. Now if we interchange x and y, we can write this as f dash y minus f dash x will be less than or equal to 3 times mod of x minus y. That is, from here we can clearly say that this mod of f dash x minus f dash y, it is less than or equal to 3 times mod of x minus y. Now what we'll do is, without loss of generality, we'll assume that x is greater than or equal to y, and when we fix x and y, we'll define this t as some x minus y, and this t will be greater than or equal to 0. Now if we choose some h which lies between 0 and t, if we take this x as y plus h, we can write this as mod of f dash y plus h minus f dash y will be less than or equal to 3 times mod h. Now what we'll do is, we'll integrate both sides from 0 to t. Now we know that integral of 0 to t mod fx dx, it is greater than or equal to mod of this integral fx dx. So we'll write this mod of integral from 0 to t f dash y plus h minus f dash y dh, it is less than or equal to from 0 to t 3 mod h dh. Now if we integrate this function, we'll get this as f y plus h from 0 to t minus f dash y into h from 0 to t, it is less than or equal to 3, and this is h square by 2 from 0 to t, and it will be mod f y plus t minus fy minus f dash y into t will be less than or equal to 1.5 t square. Now t is x minus y. If we put x minus y, it will be mod of fx minus fy minus f dash y into x minus y will be less than or equal to 1.5 x minus y square, and this is what we need to prove. Mod of fx minus fy into f dash y x minus y, it is less than or equal to 1.5 x minus y square. Now B part is, find the largest and smallest possible value of f double dash x under the given condition. So for that, we'll use this condition, which is mod of f dash x minus f dash y, it is less than or equal to 3 mod of x minus y. Now we can also write this as mod of f dash x minus f dash y upon x minus y. It is less than or equal to 3. Now we'll take this limit y tends to x. Now we take limit y tends to x, then on the left hand side this expression is nothing but f double dash x. So we can write this as mod of f double dash x will be less than or equal to 3. Now when mod x is less than a, x lies between minus a and plus a. So we can write f double dash x, it will lie between minus 3 and plus 3. So its smallest value is minus 3 and its largest value is plus 3. Now question number 6 is, the function is defined by the formula fx equals x square plus 1 when x is irrational and 10x when x is rational. Now at how many values of x in the interval 0 to 4 pi, f is continuous. Now if we'll take any point, then in the neighborhood of any point there will be infinite rationals and infinite irrationals. So that means this function will be discontinuous at all the points except for the points where the value at irrational is same as value of rational. So this function will be continuous at points where x square plus 1 is equal to 10x. So all we need to do is we need to find number of solution of this equation in the interval 0 to 4 pi. So we'll draw the graphs. So this is pi, 2 pi, 3 pi and 4 pi, and we'll draw the graph of y equals x square plus 1. So these two graphs, they intersect at 4 points. So number of points or number of values of x in the interval 0 to 4 pi where this function fx is continuous is simply 4.
Now in question number 9, we are given a continuous function f, and then we have defined two sets. Set T, which is set of slopes of all possible tangents to the graph of f, and then there is this set S, which is set of slopes of all possible secants, that is line joining 2 points on the graph of f. Now the first one is, if f is differentiable, then S is a subset of T. So if we take any secant, which is say fx1 minus fx2 upon x1 minus x2, then from Lagrange's mean value theorem we can say that there exists at least one point C in the interval x1 and x2 such that slope of tangent at C is equal to secant slope. So for any possible combination of x1 and x2, we always have point where tangent is equal to secant. So that means S is a subset of T. That means statement 1 is correct. So it is true. Now second is, if f is differentiable, then T is a subset of S. Now S must be a subset of T, but then T may not be a subset of S. So the second statement, it may not be necessarily true. So this second statement is false. We can take up an example also. Say for example, suppose function fx is sin x. If we find f dash 0 is cos 0 is 1. Now 1 belongs to T. But then if we look at the secant set, then sin x minus sin y upon x minus y, it is always less than 1. So 1 belongs to T, but it doesn't belong to the secant set. So that means the second statement is false. Now this third one is, if T is equal to S is equal to R, then f must be differentiable everywhere. It may not again be necessarily true. We can have a function where tangent set and secant set, they take all real values, but still that function may be a discontinuous function, as in the example of 10x. So again, statement 3 is not correct. So this is false. Now what about fourth one? Suppose it says 0 belongs to S and 1 belongs to S, then every number between 0 and 1 must also be in S. So at some point, slope is 0, and then at some other point, slope is 1. Now, since the function is a continuous function, from mean value property, we can say that slope of all possible secants will take all the values between 0 and 1. So that means statement 4 has to be true. So answer to this question is true, false, false and true.
Now in B5, we are given this function which is defined as this improper integral from 1 upon x to infinite 1 upon t square cos t dt. Now in the first part, for any x greater than 0, we need to show why this improper integral converges. Now we look for absolute convergence, then we can write this mod fx will be less than or equal to this integral from 1 by x to infinite mod of 1 upon t square cos t dt, and mod cos t is less than 1, so it will be less than or equal to this integral from 1 by x to infinite 1 upon t square dt. Now value of this integral is minus 1 upon t from 1 by x to infinite. So this is nothing but this is x. So clearly this integral, it converges absolutely. So that's your first part. And the second part says find f dash 1 upon pi if it exists and clearly indicate the basic results you are saying. Now we are given this function fx, which is this integral from 1 upon x to infinite 1 upon t square cos t dt. Now if x is unequal to 0, we can use Newton-Leibniz formula. So we can write this as f dash x. Now this is minus and it will be 1 by 1 upon x square cos 1 by x, and here it will be minus 1 upon x square. Now this minus and minus, it cancel and x square will also cancel. So we'll get f dash x as cos 1 by x, or we can write f dash 1 upon pi will be equal to cos pi, and cos pi is minus 1. So answer to this part 2 is minus 1. Now this third part is using the hint or otherwise find this limit h tends to 0 positive fh minus f0 upon h. Now in the question it says f0 is 0. So basically we have to find limit h tends to 0 positive fh minus f0 upon h, and it will be this limit h tends to 0 positive 1 upon h. Now f0 is from 1 upon h to infinite 1 upon t square cos t dt, and f0 is 0. Now we'll solve this question using by parts. So this is first function and this is your second function. Now we can write this as 1 upon h, and here it will be 1 upon t square sin t, and from 1 by h to infinite limit h tends to 0, and minus here will be this 1 by h from 1 upon h to infinite, here will be minus 2 upon t cube, and here will be this sin t dt. Now if we put t as infinite, it will be 1 upon infinite and oscillating value minus 1 to 1, so it will be 0. So here we can write this as limit, and it will be h sin 1 upon h, and we can write this as 1 upon h, and then this integral from 1 by h to infinite 2 sin t upon t cube dt. And this is actually h tends to 0 positive. Now if h is 0, it will be 0 into sin infinite, which is oscillating value minus 1 to 1. So this is 0, and we'll prove that this integral, it also converges to 0. Now again we'll use absolute convergence. So we can write mod of 1 upon h, this integral from 1 upon h to infinite 2 sin t upon t cube dt will be less than or equal to 1 upon h, and then this integral 1 upon h to infinite mod 2 sin t upon t cube, and again sin t is less than 1, so it will be less than 2 upon t cube dt. Now this is 1 by h and will be minus 1 upon t square from 1 by h to infinite. Now this is nothing but this is h, and when h tends to 0 positive, this integral also it approaches 0. So in this case, this entire limit is simply 0. Now question number 8 is, let f be a real value differentiable function on the real line such that limit x tends to 0, fx upon x square exists and is finite. Prove that f dash 0 is 0. Now it is given that f is a differentiable function. So that means it is continuous also. Now if the function is continuous, we can write f0 as limit x tends to 0 fx. Now we can write this limit as limit x tends to 0 x square into fx by x square. So it will be limit x tends to 0 x square into limit x tends to 0 fx by x square. Now this is finite and it is 0. 0 into finite is 0. So value of f0 is 0. Now if f0 is 0, we can find f dash 0 as this limit h tends to 0 fh minus f0 upon h. Now f0 is 0. So we can write this as limit h tends to 0 h into fh upon h square. Now fh upon h square is finite and h is 0. So from here we can say f dash 0, it must be 0. Now the next question is, a real valued function f is defined on the interval -1 to 2. A point x0 is said to be a fixed point if f x0 equals x0. Now suppose that f is a differentiable function such that f0 is greater than 0 and f1 is equal to 1. Show that if f dash 1 is greater than 1, then f has a fixed point in the interval 0 to 1. Now what we'll do is we'll consider a function hx which is given by fx minus x. Now since f is differentiable and x is differentiable, this function hx, it is also a differentiable function. Now value of h0 will be f0 minus 0 and f0 is greater than 0. So this h0, it will be greater than 0. And what about h1? h1 will be f1 minus 1, and since f1 is equal to 1, that means value of h1 is 0. Now we differentiate this function, we can write h dash x as f dash x minus 1, then h dash 1 will be f dash 1 minus 1, which is greater than 0, that is at 1. This function hx, it is an increasing function. So if we consider this function, then this is hx and this is x, this is 0. Now h0 is equal to f0 and h1 is 0, and here it is an increasing function. So this graph, it starts from some positive number and then at 1 it will be an increasing function. So that means there will be at least one point between 0 and 1 where hx is 0, and suppose this point be x0. So there will be at least one x0 in the interval 0 to 1 such that hx0 is 0. Now what is hx0? It is fx0 minus x0 equals 0. That is the value of fx0 must be equal to x0. That means this f, it has a fixed point in the interval 0 to 1. Now question number 4 is, let f be a twice differentiable function in the open interval -1 to 1 such that f0 is 1. Suppose f also satisfies fx greater than equal to 0, f dash x less than equal to 0, and f double dash x is less than equal to fx for all x greater than 0, then show that f dash 0 is greater than equal to minus root 2. Now it is given that this function f, it is a twice differentiable function So we can use Taylor's polynomial theorem. We can write fh will be equal to f0 plus f dash 0h plus f double dash theta h square upon 2, where theta lies between 0 to h. Now since f double dash x, it is less than equal to fx, we can write f double dash theta will be less than or equal to f theta. Now since f dash x, it is less than equal to 0, it simply means fx is a decreasing function. And if fx is decreasing, then f0 will be greater than f theta. So f theta will be less than or equal to f0. fh, it will be less than or equal to f0 plus f dash 0h plus f0 h square by 2. Now f0 is 1. So we can write fh, it is less than or equal to 1 plus f dash 0h plus h square upon 2. Now we know that f double dash x is less than or equal to fx. So we can say this fh will be greater than or equal to f double dash h. Now we'll integrate both sides from 0 to x. So we can write f dash x minus f dash 0 will be less than equal to x plus f dash 0 x square upon 2 plus x cube upon 6. Now we'll integrate this once again from 0 to x. Here will be fx minus f0 minus f dash 0x, and it will be less than or equal to x square by 2 plus f dash 0 x cube by 6 plus x to the power 4 by 24. Now we'll take f dash 0 together. So we can write f dash 0 x plus x cube upon 6, it is greater than or equal to minus x square upon 2 minus x to the power 4 upon 24 plus fx minus f0. Now f0 is 1 and fx is always greater than or equal to 0. So from here we can say f dash 0 into x plus x cube upon 6 will be greater than or equal to minus x square upon 2 minus x to the power 4 upon 24 minus 1. And from this we can write f dash 0 will be greater than or equal to minus x square by 2 minus x to the power 4 upon 24 minus 1 upon x plus x cube by 6. I'll be true for any x which lies in the interval 0 to 1. Now this function on the right, it is an increasing function. So this f dash 0 will always be greater than or equal to the value when the value of x is 1. So if you put x as 1, we'll get this as minus 1 by 2 minus 1 by 24 minus 1 upon 1 plus 1 by 6. So it will be minus 37 upon 28, which is nearly minus 1.32. So from here we can say this f dash 0 will be greater than or equal to minus root 2, and that is the answer to this question. Now question number 7 is, we are given this function and we have to find whether this function is continuous, differentiable, or f dash is continuous or discontinuous. Now if we look at f 0 negative, it is 0. F0 is also 0. And F0 positive, it will be e to the power minus 1 upon h. E to the power minus infinity is nothing but 0. So this function is continuous. So this function is continuous in x belongs to R. Now we'll check its differentiability. Now left hand side, it is a constant function. So f dash 0 negative, which is left hand derivative, will be nothing but 0. And what about right hand derivative? Will be f dash 0 positive, which is given by limit h tends to 0 e to the power minus 1 by h minus 0 upon h, which is 0 upon 0 form. Now we can write this as limit h tends to 0 1 upon h upon e to the power 1 upon h, which now is infinity upon infinity form. If we use L'Hopital's rule, we can write limit h tends to 0. Now this is minus 1 upon h square will be e to the power 1 upon h into minus 1 upon h square. So we'll cancel. Now e to the power minus infinite, it is nothing but 0. So left hand derivative is 0 and right hand derivative is 0. So this function is differentiable at x equal to 0. So fx is differentiable in x belongs to R. Now we have to find whether its derivative f dash, it is continuous or discontinuous. Now if we look at f dash x will be defined as e to the power minus 1 by x into 1 by x square when x is greater than 0 and will be 0 when x is less than 0. So f dash 0 negative, it is nothing but 0. And if we find f dash 0 positive, it will be this limit h tends to 0 e to the power minus 1 by h upon h square. Now this is nothing but 0 upon 0 form. Now again we write this as limit h tends to 0 1 upon h square e to the power 1 upon h, which is infinity upon infinity form. We can write this as limit h tends to 0 and L be minus 2 upon h cube e to the power 1 upon h and then minus 1 upon h square. This minus and minus will cancel. H square will cancel. We can write this as limit h tends to 0 2 upon h e to the power 1 by h, which again is infinity upon infinity form. So again, if we use L'Hopital's rule, we can write limit h tends to 0 minus 2 upon h square e to the power 1 by h minus 1 upon h square. So it will be 2 e to the power minus 1 by h, and e to the power minus infinity is nothing but 0. So at 0, left hand limit of f dash is 0, right hand limit is 0, and function value is also 0. So f dash is continuous at x equal to 0, and therefore f dash x is continuous everywhere. So answer to this question is f is differentiable and f dash is continuous, and that's your option D. Now question number 20 is, let function fx is e to the power gx and gx is sine mod of x square. Now we know that mod x is either minus x or plus x, but there is an even power. So even if we'll take minus, it'll again be plus. So we can write this gx as sine square x, and then this function fx will be e to the power sine square x. Now exponential functions sine square and x square, they are all continuous and differentiable. Now this function g, it is differentiable at all x, and that's your option number D. Now question number 16 is, consider real valued function f satisfying fx plus 1 equals fx for all x belongs to R. That means this function is periodic with period 1. We are given that gt is this integral from 0 to t fx dx, and we have defined this function ht as this limit n tends to infinite g t plus n upon n. Now if we look at gt plus n will be nothing but 0 to t plus n fx dx. Now we can write this as this integral from 0 to n fx dx plus n to n plus t fx dx. Now this function is periodic with period 1. So we can write this as n into this integral from 0 to 1 fx dx, and then plus, now this is from nt to nt plus a, and it will be from 0 to t fx dx. So we can write this function h as this limit n tends to infinite n, this integral from 0 to 1 fx dx plus this integral from 0 to t fx dx upon n. Now we split it in two parts. This n and n will cancel, and 1 upon infinite will be 0. So this ht will be nothing but will be this value from 0 to 1 fx dx, which is a constant function. So this ht, it is defined for all t belongs to R, and it is independent of t, and that's here option C. Now question number 3 is, let this function f be defined from R to R such that mod of f x plus y minus f x minus y is always less than or equal to y square. Now we need to show that fx is x by 2 plus c, where c is a constant. Now what we'll do is we'll try and rearrange this functional equation. So we'll let this x plus y as some t plus h and x minus y as t. Now we subtract the second from first, we'll get y as h by 2. So we can write this as mod of f t plus h minus ft minus h by 2, and will be less than or equal to h square by 4. Now mod x is less than a, then x lies between minus a and plus a. So we can write minus h square by 4. It is less than or equal to f t plus h minus ft minus h by 2, and will be less than or equal to h square by 4. Now we'll add h by 2. So we can add h by 2 minus h square by 4 will be less than f t plus h minus ft, and will be h by 2 minus h square by 4. Now we'll divide everything with h, and we'll take this limit h tends to 0. Now this value, it is 1 by 2. Now this is nothing but this is f dash t, and this limit, it is also 1 by 2. So from here we can say this f dash t, it is 1 by 2. Now we integrate this function, we write ft as 1 by 2 plus c, or we can write this function fx will be simply x by 2 plus c, where c is a constant. And this is how we solve such question. Now question number 4 is, let f and g be two non-decreasing twice differentiable functions. So that means f dash is greater than equal to 0 and g dash is also greater than equal to 0, such that f double dash x is equal to gx and g double dash x is equal to fx. Then suppose that
fx gx is linear on x on AB, then show that we must have fx equals gx equals 0 for all x belongs to AB. Now it is given that fx into gx, it is a linear function, say px plus q. Now we'll differentiate, we'll get f dash g plus g dash f and L be equal to p, and we'll differentiate again, we'll get f double dash g plus f dash g dash plus g dash f dash plus g double dash f and L be equal to 0. Now f double dash x, it is gx, and g double dash x is fx. So we can write gx square plus 2 f dash x into g dash x plus fx whole square and L be equal to 0. Now this is 0 or greater than 0. Fx square is also 0 or greater than 0, and f dash x is greater than equal to 0 and g dash x is greater than equal to 0. So this is also greater than or equal to 0. Now sum of positive real numbers, it cannot be 0. It can only be 0 if each of them are individually 0. So it simply means that this function gx is 0 and fx is 0 when x lies between a and b. And this is how we solve such questions.
Now this third question is, we are given that fx plus 1 equals 1 by 2 fx. Now let an equals from 0 to n fx dx. We need to find this limit n tends to infinite an. Now in this equation, if we put x as x plus n minus 1, then we can write fx plus n as 1 by 2 f x plus n minus 1 will be equal to 1 upon 2 square f x plus n minus 2, and using iteration will eventually come to 1 upon 2 to the power n into fx. Now we need to find this integral an, which is from 0 to n fx dx. Now we need to find this limit n tends to infinite an, which is this summation r varies from 0 to infinite integral from r to r plus 1 fx dx. Now what we'll do is, we'll replace x with t plus r, then we can write this as this summation r varies from 0 to infinite, here will be from 0 to 1 ft plus r dt. Now using this relation, we can write f t plus r as 1 upon 2 to the power r into ft. So it will be this summation r varies from 0 to infinite 1 upon 2 to the power r, then this integral from 0 to 1 ft dt. Now this is nothing but an infinite gp. Now sum of this gp will be a upon 1 minus r into this integral from 0 to 1. Now ft dt is same as fx dx. So we can write this as 2 times this integral from 0 to 1 fx dx, and that's your option D. Now in question number 22, it says f be any twice differentiable function such that its second derivative is continuous, and f dash x, it is unequal to 0 for all x unequal to 0. Now if limit x tends to 0, fx upon x square equals pi, then which of the following is correct? And this we have also proved in one of the previous papers. I think that was 2010 or 2011 paper, where we have proved that value of f0 will be 0 and f dash 0 will also be 0. Now if it is 0 upon 0 form, then we can write f double dash 0 upon 2 will be equal to pi, that is f double dash 0 will be simply 2 pi. Now since f dash 0 is 0, that means x equal to 0 is a critical point, and f dash 0, it is greater than 0, that means this x equal to 0 is a point of local minima. So at 0, this function will be concave up, and it will also have a point of local minima at x equal to 0. And since fx is unequal to 0, that means at no other point it will have a critical point. So this is the only critical point possible in this case. So at 0, we have a double root, that is concave up. Now after x is greater than 0, this function will increase because there is no other critical point. And on the left hand side also, this function will be a decreasing function. This function cannot increase when x is less than 0 because it will contradict our given condition where f dash x is 0 and f double dash x is positive. So this f0, it is the least possible value of this function. That means fx is greater than f0 for all x unequal to 0, and that's your option A. Now question number 30 is we have to find its continuity and differentiability and continuity of its derivative. Now f0 will be 1 minus cos 0 1, so it will be 0 into oscillating value minus 1 to 1, which is 0. So this fx will be continuous at x equals 0. Now if you find f dash 0, it will be limit h tends to 0 1 minus cos h upon h into sine 1 by h. We multiply by h and divide by h. So it will be 0 into 1 by 2 into oscillating value minus 1 to 1, which is 0. So this function is both continuous and differentiable in x belongs to R. Now we have to find continuity of its derivative. Now if we find f dash x, it will be 1 minus cos x into cos 1 by x into minus 1 upon x square plus sin x into sin 1 by x. Now if we find f dash 0 positive, it will be, now this is 1 minus cos x upon x square, which is minus 1 by 2, and this is cos infinite, which is oscillating value from minus 1 to plus 1, and this right hand side will be 0 into oscillating value minus 1 to plus 1. So we are getting this value as oscillating value between minus 1 by 2 and plus 1 by 2. That means this function is differentiable, but its derivative is discontinuous, and that's your option C. Now from tomorrow onwards, again I'm traveling, so I don't know when I'll be able to solve the UGB paper, but I'll try to do it as early as possible. Now here the function fx is defined as x plus 1 signum x square minus 1. Now signum function, it can only take three values, 1, minus 1 and 0, depending on whether this function is greater than 0, less than 0 or equal to 0. Now we look at x square minus 1, then when the value of x is minus 1 and plus 1, the value of this function is 0. In that case, the value of this signum function will be 0. Now when x is less than minus 1, this value is positive. And when x is greater than 1, again this value is positive. So in that case, this value will be 1. And between minus 1 and plus 1, this value will be minus 1. So we can write this function fx as x plus 1. Now when x is less than minus 1, this value is positive. So we can write this as 1 when x is less than minus 1. Now between minus 1 and plus 1, the graph of the function lies below y-axis. So this signum function will be minus 1. So we can write this as minus x plus 1, and when x is greater than 1, in that case, the signum function is again 1. So this value will be x plus 1. Now at minus 1 and 1, value of this function is 0. So signum function will take the value 0. So here this function will have this value 0. Now what we'll do is, we'll draw the graph of fx. Now when x is less than minus 1, so at minus 1 this value will be 0. At minus 2 this value will be minus 1. So we'll have this straight line. So this is x plus 1. At minus 1 this value is 0. Now here also this value is 0. And at 1 this value is minus 2. Now value at 1 is 0. At 1 positive this value is 2. So that is the graph of fx. Now this graph, it is discontinuous at x equals 1. So the number of discontinuities of this function is only 1, and that's your option D. And question number 29, it says this gx function is defined as this integral from minus x cube to plus x cube ft dt, where ft is greater than 1 for all real t. Then we need to find which of the following option is correct. Now we are given this function gx as this integral from minus x cube to plus x cube ft dt. Now we can find g dash x, and g dash x will be fx cube into 3x square, and then minus f minus x cube into minus 3x square. Now here we can take 3x square common. We'll get fx cube plus f minus x cube. Now for this function f, it is always greater than or equal to 1. So this value, it is always greater than or equal to 2, and 3x square is always greater than or equal to 0. So that means this function gx, it is strictly increasing function. Now if we consider g minus infinite, this value will be infinite minus infinite ft dt, and g infinite will be from minus infinite to plus infinite ft dt. Now since it is strictly increasing function, this value, it must be negative, and this value, it must be positive. And this integral from minus infinite to infinite fx dx, it approaches infinite, as ft is a positive function. So this gx, it takes value from minus infinite to plus infinite, and it is strictly increasing. So if we consider this condition gx equals c, then if we draw a line at y equals c, this line, it will intersect the curve every time at one place. So answer to this question is, for any real number c, the equation gx equals to c has a unique solution, and that's your option B. Now question number 26 is, we are given this function f x minus y equals fx upon fy. Now this condition, it is satisfied by exponential function. So here this fx, it must be a to the power x. Now if we find f dash x will be a to the power x log a. Now f dash 0 will be a to the power 0, which is 1, and then log a, and f dash 0 is p. So from here we can say value of log a is p. Now if we find f dash 5 will be a to the power 5 log a, and it is q. Now log a is p. So from here we can write a to the power 5 equals q by p. Now we need to find the value of f dash minus 5. Now f dash minus 5, it will be a to the power minus 5 into log a. Now 1 upon a to the power 5 will be p by q, and log a is simply p. So this value will be p square by q, and that's your option D. Now the fourth question is, let a, b and c be unknown constants. Consider the function fx. Now we need to write the values of a, b and c such that f double dash x exists for all real x. Now for f double dash x to exist, the function should be continuous, and this function is continuous everywhere. We just have to check its continuity at 0. So if we write f0 negative is c, and f0 positive will be log 1 0. So if we compare it, we'll get the value of c as 0. And then its derivative should also be continuous. So if we find f dash x will be 2ax plus b when x is less than or equal to 0, and here will be 1 upon 5x plus 1 into 5 when x is greater than 0. Now left hand derivative at 0, it is b, and right hand derivative at 0, it is 5. That means value of b, it must be 5. And for its second derivative, again left hand limit must be equal to its right hand limit. That means if we find f double dash x, which is 2a when x is less than equal to 0 and minus 25 upon 5x plus 1 square when x is greater than 0, f double dash 0 negative is 2a and f double dash 0 positive is minus 25. If we compare it, we'll get the value of a as minus 25 by 2. So value of a is minus 25 by 2, b is 5 and c is 0. We are given a function fx which is sine inverse of sine pi x. Now write the values of the following. Now what we'll do is we'll draw the graph of sine inverse of sine pi x, and for that we'll draw the graph of sine inverse of sine x. Now this is pi by 2 and this is minus pi by 2. This is pi, 2 pi and 3 pi. This is pi by 2, 3 pi by 2 and 5 pi by 2. Now this is the graph of sine inverse of sine x. If you have to draw the graph of sine inverse of sine pi x, we have already discussed it in transformation of graphs, that all we need to do is we just have to divide everything with pi. So here it will be 1 by 2, this one is 1, this is 3 by 2, this is 2, this is 5 by 2 and this is going to be 3. Now we need to find the value of f 2.7. Now 2.7, it will lie in this region, and in this region we have to find equation of this line. Equation of this line will be minus pi x, and then this graph, it is going to intersect at 3 pi. So when x lies between 2.5 and 3.5, in that case this fx, it is defined as 3 minus x into pi. Now we need to find the value of f 2.7. Now f 2.7 will be 3 minus 2.7 pi, which is 0.3 pi. You can also find the equation of this straight line using coordinate system. So this point is 5 by 2 comma pi by 2, and this point here is 3 comma 0. Now using 2-point form, we can find equation of this straight line. Answer to this first question is this is 0.03 pi. Now we differentiate it. We'll write f dash x, and f dash x will be simply minus pi. So at 2.7, its derivative will be simply minus pi. Now we need to find value of this integral from 0 to 2.5 fx dx. Now from symmetry, these two integrals, they'll cancel out. The only integral value that we'll have is this triangular region, which is 1 by 2 into, now this is 1 by 2 and its height is pi by 2. So it'll be simply pi by 8. And fourth one is the smallest positive x at which derivative does not exist. So this function is not differentiable at this point. So the smallest value is at x equals 1 by 2. So here this one is going to be x equals 1 by 2. So answer to this question is 0.3 pi, minus pi, pi by 8 and 1 by 2. Now question number 13 is an even function has left derivative at x equals 0. So that means f dash 0 negative, it is 5. Now we need to find its right hand derivative. We know that a function is even if f of minus x is equal to fx. Now we'll differentiate this function. We can write f dash minus x into minus 1 is equal to f dash x. Now we'll replace x with 0 plus h. Then we can write minus f dash minus h is equal to f dash plus h. Now this is f dash 0 negative and this is f dash 0 positive. So f dash 0 positive will be minus and then f dash 0 negative, which is left hand derivative, and it is minus 5. So right hand derivative of fx at x equals 0 will be minus 5, and that's your option number C. Now question number 28 is we are given two functions fx which is 1 when mod x is less than equal to 1, and 0 when mod x is greater than equal to 1, and gx, which is 1 when mod x is less than equal to 2, and 2 when mod x is greater than equal to 2. We have defined two functions h1 and h2, which are compositions of f and g. Now we'll take h1x. h1x is f of gx. So we'll take this function fx. We can write f of gx as 1 when mod of gx is less than equal to 1, and it is 0 when mod of gx is greater than 1. Now looking at the value of gx, so gx is 1 when mod x is less than equal to 2. So that means we can write h1x as 1 when g1x is equal to 1, that is when mod of x is less than equal to 2, and it will be 0 when gx is 2, that is when gx is greater than 1. So it will be when x is greater than 2. So this function, it is discontinuous at x equals plus or minus 2. So h1x, it is discontinuous at plus or minus 2. Now what about h2x? Now h2x is g of fx. Now g of fx will be 1 when mod fx is less than equal to 2, and will be 2 when mod fx is greater than 2. Now fx can take the value 1 and 0. So that means it cannot take the value greater than 2. So the only option that we have here is g of fx will be 1. So this h2x, it is nothing but a constant function. So this function will be continuous for all x belongs to R. So answer to this question is h1 is discontinuous at plus minus 2 and h2 is continuous. So h2 is continuous everywhere and h1 has discontinuity as plus minus 2, and that's your option number C. Now question number 24 is, let f from R to R be a continuous function such that limit n tends to infinite f and x exists for every x belongs to R, where f and x is composition of f n times for any n greater than or equal to 2. We have defined two sets. Set S as limit n tends to infinite f and x for x belongs to R, and then the set T, which is fx equals x for x belongs to R. Now we'll start with this limit. Limit n tends to infinite f n x, and let it be some function, say hx. Now since f is continuous, we can write this hx as f and then limit n tends to infinite f n minus 1x. This limit n tends to infinite f n minus 1x will again be hx. So from here we can write hx is equal to f of hx, which again is of the form x equals fx when x lies in range of fx. So our set S is x equals fx for any x which lies in the range of fx. Now the set T, it is given as x belongs to R and fx equals x. Now both these sets, they look equal, but then here the crucial information is this S is when x lies in the range of fx. So essentially this S, it has to be subset of T. So answer to this question should have been S is a subset of T. ISI has given the answer as C, which is S equals T, considering x equals fx as same for both the functions. But then it is entirely up to the interpretation. Now question number 25 is, for this function we need to find its continuity, differentiability and continuity of f dash. Now limit x tends to 0 positive e to the power minus 1 upon x will be e to the power minus infinite, which is 0, and f 0 negative equals f0 is also 0. So that means fx is continuous at x equals 0. So this function, it is continuous. Now what about its differentiability? F dash 0 negative will be simply 0. We'll find its right hand derivative. F dash 0 positive will be limit h tends to 0 e to the power minus 1 upon h minus 0 upon h. So we can write this as limit h tends to 0, 1 upon h upon e to the power 1 upon h. So which is infinity upon infinity form. We can use L'Hopital's rule. So it will be limit h tends to 0 and then it will be minus 1 upon h square e to the power 1 upon h and minus 1 upon h square. So it will be 1 upon e to the power infinite, which is 1 upon infinite, it should be 0. So left hand derivative is 0, right hand derivative is 0. So that means fx is differentiable at x equals 0. Now what about continuity of f dash x? So we'll find f dash x will be e to the power minus 1 upon x and then plus 1 upon x square, which is not defined at 0. So this function is continuous and differentiable, but f dash is not continuous, and that's your option number C. Now question number 71 is, again we are given a function in two variables and we have to find its continuity and its partial derivative with respect to x. Now we'll find this limit xy tends to 0, 0. So it'll be this xy. Now we'll put xy is 0, this is 0. So this limiting value is 0, which is not equal to f 0, 0, which is given as 1. So this function is not continuous at 0, 0. Now we'll find fx at 0, 0 will be this limit h tends to 0 f h, 0 minus f0 upon h. So it will be simply this limit h tends to 0, f h0 will be 0 minus f0 is 1 upon h, and this value it tends to minus infinite. So that means this function is not continuous and partial derivative does not exist. That's your option number D. Now question number 72 is, we are given this function fx and it is given that this function is differentiable at x equal to 0. We need to find this condition. We can write this function fx as a0 cos x minus a1 sin x minus a2 x cube when x is less than 0, and it will be a0 cos x plus a1 sin x plus a2 x cube when x is greater than or equal to 0. f0 negative, it will be a0 and this is 0, so it will be a0, and f0 positive will also be a0 and the value at 0 is also a0. So this function is continuous at x equals 0. Now we will differentiate this function. We can write this as minus a0 sin x minus a1 cos x minus 3a2 x square when x is less than 0, and it will be a0 minus sin x plus a1 cos x plus 3a2 x square when x is greater than 0. Now we'll find f dash 0 negative. F dash 0 negative will be, this is 0, this is 0, so it will be simply minus a1, and f dash 0 positive will be plus a1. Now since this function is differentiable, so minus a1 must be equal to a1. So from here we'll get the value of a1 should be 0. So answer to this question is, this map will be differentiable if the value of a1 is 0. Now question number 73 is, if a function fx is a differentiable function such that limit x tends to infinite fx is 1 and limit x tends to infinite f dash x is alpha, we need to find the value of alpha. Now what we'll do is, we can write f n plus 1 minus fn as fn plus 1 minus fn upon n plus 1 minus n. Now this is nothing, it is slope of this function at some point. This is equal to some f dash c where c belongs to n comma n plus 1 using Lagrange's mean value theorem. Now we'll take this limit n tends to infinite f n plus 1 minus fn. It will be this limit n tends to infinite f dash c. Now when n tends to infinite, this limit, it is equal to 1. So it is 1 minus 1, and then this limit, which is limit n tends to infinite, f dash c. Now when n tends to infinite, this c also tends to infinite. So basically this n tends to infinite, f dash c is nothing but alpha. So this is alpha. So from here we can say value of alpha, it must be 0, and that's your option number A. Now question number 74 is, we are given two functions such that f dash x minus g dash x is less than equal to 0 when x is less than 1, and f dash x minus g dash x is greater than equal to 0 when x is greater than 1. Now we need to find relationship between fx and gx. So we'll consider this function hx, which is fx minus gx. Then we can write h dash x as f dash x minus g dash x. Now we'll consider this first case when x is less than 1, that is when f dash x minus g dash x is less than equal to 0. So here we can say this h dash x is less than equal to 0, implying that hx is a decreasing function. Now if hx is decreasing and if x is less than 1, then hx is greater than h1. Now what is hx? Hx is fx minus gx, and it will be greater than f1 minus g1. If f1 is greater than g1, then f1 minus g1 is greater than equal to 0. So from here we can say fx must be greater than or equal to gx. So when x is less than 1, fx must be greater than equal to gx if f1 is greater than g1. Now we'll take the second case when x is greater than 1. Now when x is greater than 1, h dash x, which is f dash minus g dash, it will be greater than 0. In that case, hx will be an increasing function. So when hx is increasing, if x is greater than 1, then hx is greater than h1. Now hx is fx minus gx, and it is greater than f1 minus g1. Now f1 is greater than g1, so it is greater than equal to 0. So we can write fx is always greater than equal to gx. So for both the cases, we are getting this result, which is fx is greater than or equal to gx, and that's your option number A. Now question number 68 is, we are given this function in two variables fxy as e to the power minus 1 upon x square plus y square when xy, it is not 0, 0, and it is 0 when xy approaches origin. Now first we'll check whether this function is continuous at 0, 0. So now if we'll take this limit, which is limit x, y, it approaches 0, 0, we can write this as e to the power minus 1 upon x square plus y square. So it will be e to the power minus infinite, which is 0. Now f 0, 0 is also 0. So we can say that this limiting value is equal to f 0, 0. So that means this function is continuous at 0, 0. Now we look at its first order partial derivatives. Now we can write fx 0, 0 as limit h tends to 0 f h, 0 minus f 0, 0 upon h. So it will be this limit h tends to 0. Now what is f h, 0? It will be e to the power minus 1 upon h square minus 0 upon h. Now this limiting value is also 0. In the same way, we can show that f y 0, 0 is also 0. So that means this function, it does have first order partial derivatives. Now we need to check whether this function is differentiable or not differentiable. So from definition, we can say that this function will be differentiable when this limit h, k tends to 0, 0, and it will be e to the power minus 1 upon h square plus k square, because partial derivatives, they are all 0 and function value is also 0, upon under root of h square plus k square, which is same as e to the power minus t upon under root t when t tends to 0. And this limit again it tends to 0. So that means this function is differentiable at 0, 0, and that's your option number D. Now question number 69 is, consider this function from 0 to x, 5 plus 1 minus y dy when x is greater than 2, and then 5x plus 2 when x is less than or equal to 2. Now we need to find whether this function is continuous and differentiable at 1 and 2. Now we know that its definition changes at 2. Now we'll find f2 negative. f2 negative will be 5 into 2 negative plus 2, that is nothing but 12. Now we'll find f2 positive. f2 positive will be this integral from 0 to 2, 5, and then mod of 1 minus y dy. Now this is 5 integral from 0 to 2 dy, and then plus 0 to 2 integral of 1 minus y dy. Now this is 5 into 2, and then plus from 0 to 1 1 minus y dy, and then from 1 to 2 y minus 1 dy. So it is 10, and then here it will be y minus y square upon 2 from 0 to 1, and plus y square upon 2 minus y from 1 to 2. So this is 10. Now here it will be 1 minus 1 by 2, and here it is 1 plus 1 by 2, and it will be 4 minus 1, and then minus 2 minus 1 is 1. So here 1 and 1 will cancel. So we'll get this as 10 minus 1 by 2 plus 3 by 2, which is 11. So left hand limit is 12 and right hand limit is 11. So this function is not continuous at x equals 2.